Coming to the boosting part, till now we were trying to understand regarding the different bagging methods. So if you see, coming to the ensembling part, so ensembling is nothing but instead of using a single classifier, we are going to use multiple classifiers or multiple models. Why we are using that, that we will see in the upcoming slides, but basically we are trying to do that. And in ensembling itself, you have two different types of algorithms that we primarily talk of. Those two belongs to, one is regarding the bagging and one is regarding boosting. In whatever the random forest algorithm that we have discussed previously, it is nothing but it comes under the bagging method. And now we are going to discuss regarding the boosting part, and already we had an understanding of a decision tree classifier. So up to the prior knowledge whatever we have, and the prior understanding, we are going to proceed further and going to understand more into the things regarding the ensembling based methods, particularly the boosting part. Okay, so yeah, we will get started on this. So yeah, so coming to the goal of machine learning problem, so what exactly we are trying to do in machine learning? In machine learning, we have some set of samples, observed samples, and we are going to create a parametric function, a prediction function, which maps your input sample to the output, right? So whatever the x is there, you are mapping this x to your yi. Xi is mapped to the yi, and you are using something called a parametric function, which is your f of yi. Which is our model that we are constructing. And if you give some after the trained model, like once the model is trained, in the sense like the parameters are adjusted accordingly with respect to the training it has received. Now if you give your xi to whatever the f of xi model that has been trained, you are going to get your yi, which is your prediction that is expected. So that is what we are trying to do in machine learning, right? And whatever the error that is obtained with you, so you want to minimize your error function or the loss function, right? So yeah, so this is what your loss function that we have formulated with respect to the expected value of the loss. And this is what this is your empirical risk or the minimum risk that you have to minimize. And yeah, so what are the components of machine learning algorithm? So machine learning comprises of the representation and strategy and optimization. So representation is nothing but we are going to change our respective values, right? In the sense like if it is linear regression, what are the parameters at our hand? We have beta naught and beta 1. So we are going to adjust your beta naught and beta 1 respectively in such a way that you are going to minimize your loss function. So you want to minimize your loss function. And for minimizing the loss, what are the things at hand with us? We have the coefficients beta naught and beta 1, or the respective weights that are present, or the parameters that are present with us. So we have to change our parameters in such a way that your loss is sort of minimize it. So that is representation, whatever the function optimization problem. And you are going to use some optimization algorithm to do that, right? It may be gradient descent or any advanced descent algorithms like SDD or ADAM kind of algorithms you are trying to use to minimize this loss function. So how are you minimizing the loss function? In the sense you are going to use some optimization algorithm to minimize the loss function or the cost function. So yeah, so that is what yeah, so we search optimal prediction function by minimizing loss. That is the optimization part. And strategy is nothing but we are defining a loss function so that we can evaluate the error between the whatever the predicted value is there and the response value that has been obtained. If you see in the regression case, we saw the mean square error as our loss function, right? And in the classification part, if you see, we have something called this categorical cross entropy that you have defined. We have the binary categorical and binary cross entropy as well, which we have defined. And then we are trying to minimize that particular loss function. So this is how we are going to proceed with the ML part, how we are going to perform the ML in the sense like whatever the training that we are trying to do. And coming to the representation, so if you see the representation, what we are doing here, we have a hypothesis space of prediction function. If you take a model can be a linear model or a tree-based model or additive model and a Bayesian network. So there are different types of models that are there. In the sense like if you take a model, it should have the expressiveness and it should have the generalization ability also. So if it is not generalizing, then what happens? It will overfit, right? So that we have to avoid. So it should be expressive, and along with that, it should generalize also. So yeah, so when you're choosing a model, you have to consider different set of things. So we have to consider about the learning problem, and we have to consider the difficulty of the learning problem. So what is the learning problem, or what is the data at hand with you? And once we have that, what is the characteristics of the data? Is it linear or not linear, or what is the relationship between the data of x and y? That's the reason we are trying to use this scatter plots and all different EDA, right? So want to understand the relationship between the data, and also assess the data itself, so that we can try to find some appropriate model out of all these different set of models which works well. And that is one side, and one more side is if you have already good amount of knowledge and experience in the domain or in the machine learning field, then obviously for a particular data set you should be with your prior experience, you should be able to figure out which model works better, right? So if you see a particular data set, you should be able to figure out that okay, logistic regression will perform well, or a random forest will work well on this kind of problem. So that comes from experience. If you have dealt with lot of problems which are similar, and suddenly you have encountered a similar problem, then you can do that. And depends on the data also, as I told, how many samples you have, how much data you have, and how many features you have, and what is the interaction between the features, and is there any are there any outliers that are present in the data? So there are different set of factors that we are going to consider when we are trying to choose a particular model, and also the requirements that we have, in the sense like what is the model interpretable. So if you see some kind of models, they are black box models, in the sense like if you see neural network, it is not interpretable model, but you may get some reasonably good accuracy compared to other types of models. But if you have the interpretability as a primary criteria, then it's better to choose a model which is interpretable. And also the computational cost, and how much computational intensive that particular algorithm is, or whatever the constraints that you have to take these constraints and requirements also into consideration when you are trying to choose a particular algorithm for your data. And coming to the strategy part, we have to distinguish the good classifiers from bad ones in hypothesis space by defining a loss function. In the sense like we are defining our loss function first, and also we have discussed some sort of loss functions. So in classification, we have discussed about the logarithmic loss function, which is a log likelihood. And also there are different types of loss functions as well. You have these exponential loss function and hinge loss functions. And in regression, we were discussing about the absolute loss function and the quadratic loss functions. And yeah, there is something called this Huber loss function also. So we have these different types of loss functions. So there are many. But we once we formulate that, we have to we have first thing is we have to formulate your loss function, and we have to use some sort of optimization algorithm, a first order optimization descent algorithm, for finding the minimum value for that loss function. So using some optimization method, first you are visualizing your loss function, and you are trying to find a global minima for that particular loss function. So this is what we are trying to do in the training part. And why we are using regularization? Regularization is nothing but the intentional bias that we are inducing into the model, so that your model is not overfitting and it generalizes well to the data. This is what regarding regularization that is added to the loss function. So yeah, this is the strategy part. And if you see the loss function, so you can see the loss function that is defined here, and you can see this is the binomial logarithmic loss function, which we have already derived, and we have had a comprehensive discussion when we are discussing the logistic regression part, right? Also we saw the coding part of that as well. So this is the loss function generally that we are going to use for binary classification part. And what are the loss function that we have defined, as I have mentioned at that time, that we are doing a maximum likelihood estimation. and it is whatever the MLE is there, it is something similar to the cross entropy. That is the reason we were defining this particular loss as a categorical entropy loss or the binary cross entropy loss. And what are the components of typical algorithms? So if you see linear regression, you have a linear model and you have a spared loss, and it has a closed solution directly, whatever the mean square solution that we are trying to get. And if you see the logistic regression case, you have a linear function and a logit. So we have a logarithmic loss that we have defined, and we have to use gradient descent kind of optimization algorithm. Even for the ANNs, which are the general neural networks, right, artificial neural networks, that also has a logit link, and even for that also you need a gradient descent kind of optimization algorithm. And you see this other set of algorithms, right? So respectively, like some of them we are yet to discuss, right? So respectively, whatever the type of model that we have taken, we have the representation part, how we are going to represent your model, and then how we are going to calculate the error between error function or the loss function. And once you have formulated that, what is the optimization function that we are going to use to minimize that particular loss function? That also has some dependency, right? In the sense, with respect to this type of loss function, you are going to use this type of optimization algorithm. So that is also one thing. So this is what this represents. And yeah, so there are some terms which you don't know, but as of now, just ignore those things. So that I just want to show you that this is how the flow of the ML problem definition, and how we are going to do the training part, and how we are going to do the formulation part. So you can take the example of the linear regression and logistic regression, which you are familiar with as of now. Okay. And then now we are trying to understand the bagging and boosting part. So if you see the error part, whatever the error is there or the loss function that we have defined across, it can be again decomposed into two things: bias and variance. So if you have an unbiased estimator, then your bias value will be 0. So again, there are different types of estimators like blue estimator, unbiased estimator, so minimum variance estimator. So there's a lot of underlying theory that is there, but it is not required for us to go very in depth into this, but just try to understand that whatever the type of loss function that we have, it has a decomposition, and it consists of the bias and variance part. So ideally, whatever the estimator that we are trying to construct or model, it should have low bias and low variance. This is the ideal condition. So you see, this is the ideal condition. Even you can look into it and you can understand, right, that this looks ideal. But if you see you have higher bias, so you have low variance but high bias, you can see the shift here. And if you see high variance and low bias, so you can see the variance here. So whatever the samples are there, they are spread across, right? So again, that is one problem. So bias is nothing but the added term. So all the values are sort of like near to each other or closer, but you have additional bias that has been added to every component. And variance is nothing but if you see, it is at the targeted value or the value that is intended, but there is a spread in the data. So the distribution of the data is not uniform, or the samples are not uniform, so they are spread across. So that is what variance refers to. So yeah, so this is again the worst case, in the sense like high bias and high variance, which is not at all required for us. So finally, you have to understand that this is the case that we have to require, that is required, or we want to model ideal classifier which has this. It should have low variance and low bias. Then you can tell that okay, this model is good, and it can perform better. A statistical estimator, ideal statistical estimator that we want to construct for a particular type of samples or data that we have at hand. And these both are ensemble based techniques. So bagging or boosting are ensemble based techniques. And if you see random forest, so it is a bagging based algorithm. So you have understood that there's a collection of decision trees, and with respect to that, it does some random feature sampling, and from that it is going to perform the bootstrapping, and we do the bootstrap aggregation, and finally we'll use a voting procedure to finally conclude a particular particular class or using the voting procedure that we do, we are going to assign our particular X sample to a particular Y class that has been defined if it is a classification problem. So this is how we are going to deal with a random forest classifier or a bagging based classifier. And in boosting also also an ensemble based technique, and this is also with respect to the decision trees. So even in bagging we have decision trees, and even you have in boosting also we have decision tree as our base learners. So we will understand more regarding the boosting in the upcoming slides. So yeah, where a set of weak learners are combined to create a strong learner that obtain better performance than a single one. So instead of using a single decision tree, if you have like as a decision tree is also a classifier, right? So you can use a decision tree also. But instead of that, we are trying to use these ensemble based models because as they perform better than the individual decision tree or the individual classifier. So we have these collections of classifiers, and with respect to that, we are performing our classification. And moving further, so bagging is short for bootstrap aggregation. So as we have already saw how this bootstrap aggregation is done in random forest algorithms, it's a way to increase accuracy by decreasing variance. How we are going to decrease our variance when you are you are constructing your bagging algorithms, in the sense if you consider the random forest itself, then what you are doing, instead of taking a decision of one classifier, we are using n number of classifiers or decision trees, and from that we are using some aggregation or voting procedure, and from that we are calculating our output. Because of that, whatever the aggregation that we are doing, it is decreasing your variance. Instead of collecting your output or classifier response from one decision tree, you are taking an ensemble of decision trees or collection of decision trees, and you are depending, or you are taking your decision with respect to this multiple decision trees. Because of that, and you are aggregating or averaging across the classification results, and then you are taking your output. That is the reason it decreases your variance. Yeah, develops fully grown trees, low bias, high variance, which are uncorrelated to maximize the decrease in variance. Mm, yeah, so a decision tree itself has high variance, but we are using a collection of decision trees so that, yeah, which are uncorrelated to each other to decrease the variance. So what we are going to do is we cannot reduce the bias, but we can decrease the variance in the whatever the bagging case that we have discussed. That is the reason we require large unpruned trees. So whatever the pruning also we have discussed, right? After this part, we are going to do the pruning also, so that we can improve our model, or it's also a part of the model construction part, right, when we are discussing that. So yeah, so this is what regarding the bagging part. And moving further and try to understand the boosting part, so it's a way to increase accuracy by reducing bias. So here, instead of reducing the variance part, previously what we are doing in the bagging part, there we are trying to reduce our variance. Here we are trying to reduce our bias. So we have this two-step process done. So what we are doing is develop averagely performing models or subset of the original data. So we are developing some models which are averagely performing, and now what we are going to do is we are going to boost the model performance. So by combining a cost function, so that we will see what is the cost function that we are defining with respect to the type of boosting algorithm that we are choosing. But basically what we are trying to do is we have a weak learner. So initial weak learning classifier is there with us. So it has performed some classification, and you got some errors with respect to that, and with respect to that, whatever the misclassifications it has done, you are going to take the data, whatever the misclassified data is there, and then you are going to again give some weightage, or you are going to feedback your data to this model, and with respect to that weightage, again you are going to train your model, and now your model has improved a bit. So compared to the previous accuracy, you got some higher accuracy, and now again you are doing the same thing, in the sense like again you are giving some weightage to the data, and again you are feeding it, and again you got some more higher accuracy. So slowly what is happening is whatever the weak decision whatever the weak classifier or weak decision tree collection that you are taking, you are, that is they are becoming strong learners. So whatever a weak learner is there, iteratively we are converting or we are transforming our weak learner to a strong learner. This is how we are going to perform the boosting part. So it is like the basic overview of that, but we are going to discuss in depth into all the respective boosting algorithms that are present, which are mostly used. And yeah, so develops shallow decision trees, aka weak learner. So we have a weak learner which has high bias and low variance, and you are going to take that and slowly iteratively you are going to reduce your bias. So whatever the error reduction is there, it is mainly focusing on reducing the bias part and developing a new learning taking into account the previous learner. So sequentially, and one more thing is, we are going to see it further that bagging is a parallel based algorithm. Like if you see, it works parallelly, and boosting is a sequential algorithm. So you have a weak learner, and in next iteration it become a bit stronger, or a bit stronger, and in the next iteration more stronger. Iteratively you are going to transform your weak learner to a strong learner. So that is what the concept behind boosting. And yeah, so we have the single learner, and you have the bagging which have n learners, and in the boosting also n learners, which are your ensemble based algorithms. And you have the complete training set. Here in bagging, what we are doing sample random sampling with replacement. If you remember, we have discussed that we are going to do it with replacement. And in random sampling with replacement over weighted data, as I have told you, with respect to the misclassification the model is doing, whatever the weak learner is there, we are going to give weightage to the data that concentrate more on this sample, concentrate more on this set of data, or respective samples, and we are going to feed it. So we are going to give weightage to the training samples in boosting, and that is also with respect to the replacement. And if you see, bagging is parallel, so whatever the trees that we are constructing, that we are doing parallelly, and boosting is done sequentially. So and also, like, boosting also can be parallelized. So if you see XGBoost kind of algorithm, so there is a mechanism using which you are parallelizing your boosting as well. But basically, you see, as a concept, boosting is sequential. Yeah, so if you take, you are going to have a single estimate here in the single decision tree case, and we are going to have a simple average, with whatever the voting procedure that we are discussing in the backing part. And in boosting part, we have this weighted average. So instead of considering single decision tree output, or aggregation, we are taking a weightage. So we are taking a weighted average, and then we are doing the aggregation, and that is how we are going to construct our loss function or the error function.